Okay, welcome everyone. Welcome, Adam. Thank you to be there today. So we are proud to have a really well-known speaker in our Luxembourg meetup today. So welcome, Adam, and thank you for your time. Before we start, could you introduce yourself, and then we can see what you want to talk about today.
Sure, I'm going to do that. Hello, everyone, and good afternoon. I'm Adam Tornhill, based out of Sweden, and I'm going to give a proper introduction of myself. But before I do that, let me try the most challenging aspect, and that is to share my screen. Let's see if I get that right.
Yep.
You should be able to see my screen, and you should be able to see my slide deck in just a minute. Here we go. So I'm here today to introduce and demonstrate a set of techniques that I call behavioral code analysis. And behavioral code analysis, it's a very broad topic. So there's a lot of stuff to cover. So what I'm going to do today is that I'm really just going to scratch the surface and then look at some specific topics and use cases and drill deeper into those. And I will make sure to leave plenty of time towards the end for questions. I'll be more than happy to answer any questions. And before I do that, let me introduce myself properly. So I kind of view myself as a psychological programmer. And what I mean by that is that my background is within engineering. So I'm an electrical engineer. I worked as a software developer for a long time, but also had like a parallel career. I also happen to have a degree in psychology. And I've written 2 books about this intersection between technology and the human side of it. The first one called Your Code is a Crime Scene that came out like, I think 6-7 years ago. And then my more recent book, Software Design X-Rays. And I like to spend a minute and tell you why I got interested in psychology and why I think it's relevant as a software developer. So my road to psychology started on August the 1st, 1997. What happened on that day was that I got my first job as a programmer. I was fresh out of school and joined a larger company as a software developer. And I have to admit, maybe because I was young back then, but I was a little bit overconfident. I was, very confident that I know programming. I know how to write code, right? Because at that point in time, I'd already coded for almost a decade. I started in the late 1980s on my Commodore 64. Wonderful machine, still one of my absolute favorites. So if you want to talk about that later, I'm all in for it. But anyway, I had some programming experience and I joined this large company. But I was in for a pretty rude awakening because very soon I noticed that large-scale software development is something completely different compared to what I had been doing on my own. And I felt pretty lost at the beginning. And maybe I still do occasionally. But anyway, one of the issues when I joined my first job was that no one really had time to onboard me. No one really had time to sit down and explain how the system works or what I'm supposed to do. And the reason for everyone's busyness was because they were wrapping up a large project. So this was a project that had been going on for a couple of years. They were developing new hardware and lots of new software systems to go with that. And the work was done by 5-6 different development teams. But now everyone promised me in just a couple of weeks, we will have all the time in the world for you. We can sit down with you and onboard you properly. Because there was only a single thing left to do on that project now. And that single thing left to do was to integrate it. And they had planned a whole month for integrating 2 to 3 years of development work by multiple teams. And as you can probably imagine, it didn't go too well. In fact, after 6 months, we had to pull the plug on that project. We had to restart it with a new scope because they could never get it to work. And that was my introduction to the beautiful world of large-scale software development. And from there, I have to admit, it pretty much went downhill, right? I saw one software disaster after another. And at some point, I really started to think, why is it so hard? Why it's so hard to kind of succeed with software at scale? And I kind of had a feeling that I won't find answers to that within the tech industry, because if we knew the answers, we would already be doing those things. So I decided to look elsewhere. and I decided to pick up psychology because psychology is about people like us, people who work with software. And psychology is about how we think, how we reason, how we solve problems and collaborate with others. And I kind of had this idea that all of these skills would be highly relevant in a software setting. So I spent 6 years at the university studying psychology. And what I try to do these days is kind of pull some of the lessons I learned from psychology back into my technical work. And I hope to share some of those things with you today as we go along. So that's basically my background. And yeah, I know I talked about starting out to write code for the C64 back in the day, but do I actually have any real programming credentials, right? Any professional credentials? I know I don't want you to think of me as some kind of manager or something like that, right? Because I'm still writing code. I'm not daily maybe, but a couple of times a week I sit down and write code. I've written 2 more technical books. First one was about using design patterns in the context of the C programming language. And then the second book I wrote was called Lisp for the web. And I get this question before the meetup started, what's my favorite programming language? And I have to admit it's Common Lisp. So I wrote a book about it. But of course, those books were published a long time ago. Do I have any real coding experience that I can actually show to the world? Well, let me share with you my proudest achievement. A couple of years ago, I implemented the FISPAS challenge, you know, this interview challenge in C++ compiler error messages. So I think that was like the peak of my career. But like I said, I'm still writing code. I'm still involved with it very much every single day. And I use behavioral code analysis as an important tool for me. Sorry. So with that covered, let's get to the main topic. Why do we need a new thing? Why do we need behavioral code analysis? I'm going to explain what that is in a moment. But before I go there, I'd like to point out that the reason I think we need something different is because our reality is really just a Rorschach blot. And I like to clarify that with a quote from one of my favorite psychologists, a psychologist called Bars, who says that humans seems to be driven at least as much by fantasy as by reality. And this has important implications for us as software developers, because the reality in software is much, much harder to get a grasp on. It's much, much harder to get what I call situational awareness of the software system. And the main reason for that is because if we take a step back and think about what we actually do, what is software? What is code? We will see that software lacks visibility. Software lacks physics. So there's no way we can take a software system, pull it out, turn it around and inspect it for potential flaws or omissions, right? So what happens in that case is that we fall into something called the law of expectations, which is another thing I learned about in my psychology classes. And that is whenever we humans lack certainty about what we do or about our environment, our conscious experience is very heavily determined by unsupported expectations. And that means that the investigations and decisions that we do in software are very easy to get biased, right? Because software is opaque and non-transparent. So let me show what I mean by taking you to one of my favorite psychology experiments. So what I'm going to show you now are 2 different maps. Both of them are maps over Britain. The difference is that one of those maps was drawn by a group of subjects located in the south of England in Cambridge. And the other map was drawn by a bunch of people located in Glasgow in the north, right? So let me show those 2 maps to you and see if you can guess which map was drawn in the south and which one that was drawn in the north. Here they are. So I hope you see the differences here. And of course, the map to the left, the one I'm highlighting here, was drawn by the group Cambridge in the south. And what's so fascinating is that this group, they exaggregate the distances in the south, which happens to be the areas of England that they're most familiar with. And we can see that the group in the north, they kind of made the opposite error, right? They kind of underestimated the distances in the south. So they kind of compressed the whole geography. And the reason I show you this is because we tend to do exactly the same thing when reasoning about the code base. We overestimate the importance or maybe even the complexity of parts that we're familiar with. And these biases can, seriously lead us down the wrong path. And I have so many stories to share around that if you want to ask about that later. So the number one thing I think that we need in software is to get situational awareness. So let's move over to our technical world. And let's consider a typical modern software system. A software system typically looks like this, right? It's fascinating. It's always these rectangles, isn't it? And a couple of databases maybe. So we have some kind of application logic running somewhere on a server. And then we have a bunch of different clients, a bunch of different consumers. So we have different mobile devices. We might have a desktop application. We typically have a REST API so we can communicate with other machines, and so on. So in today's world of software, it's very, very different from the way it looked back in the 1980s when I started to program. Back then, you could have a single developer write the whole game and publish it, right, an end product. And look at the games today, right? Most of them are developed by large teams, hundreds of people, right? And it's the same with our business applications. They involve so many people, and each person is typically biased by their knowledge of the parts that they are most familiar with, where they tend to do most of the work. And it becomes incredibly hard to get a holistic overview of what does our software actually look like? Where are the strong parts? Where are the weak parts? So some of the questions I hope that we can address with the behavioral code analysis is, first of all, are there any risks here? Is there any parts of this large complicated system that have started to accumulate technical debt so that I have to be aware of that? I might have to do proactive actions. And what does it actually look like from a developer productivity point of view? Are there any bottlenecks in that solution, something that hold back our efforts? And another thing that I found really, really important is for us as software developers, we can often understand, when we see overly complicated code, we know that, all right, we need to refactor this. And sometimes we need to do larger redesigns to address a deeper problem. And that typically means that we need to get the buy-in. It's very, very common. We need to get some kind of buy-in from people like maybe a product manager or product owner. And we need to tell them that, hey, we need to take a step back. We can't implement any new features in this area. What we need to do right now is to take a step back and spend a couple of weeks redesigning this thing so that we can move ahead safely. Having that conversation around something as opaque, as deeply technical as code is very challenging with non-technical stakeholders. So what if we could find a way of letting non-technical people, people that don't write code, to kind of peek into our otherwise inaccessible world of software? There have been a number of approaches over the year. One approach that I started with myself and that I see still fairly commonly used is to use different code level metrics. So some of you are most likely familiar with different linting tools, different static analysis approaches. And those kind of tools, I'm a big fan of them because I think we as developers, we need all the support we can get. So linting tools is something I use myself when writing code. It serves very well as a low-level feedback loop. But using static analysis findings to kind of reason about the system as a whole is very, very challenging. And the reason it's challenging is because what tends to happen if you pick up a linting tool or static analysis tool and you throw it at the existing code base, what tends to happen is that you get tons of findings. You get hundreds, often thousands of findings. And this is where it starts to become dangerous. Because what I've seen in several organizations is that once you're left with a list of, like, let's say 7,000 critical issues, and you're supposed to act upon it, what happens then is that the organization tends to put a quantitative goal on it. So I tend to say things like, all right, we have 7,000 major issues. We cannot fix all of them, but let's allocate a sprint, or let's allocate 2 months into bringing them down to just 5,000. And when I hear something like that, I always advise against it. Because to me, going from like 7,000 major issues down to 5,000, it's a little bit like choosing to jump from the 5th instead of the 7th floor. Most likely, none of them are a good idea. And the reason I say this is because we need to be very conscious about what kind of behavior we reinforce by putting any kind of quantitative goal on code quality or technical debt. Because what's going to happen with the quantitative goal is that we as developers, we're going to optimize for what we're being measured on. So we're going to make sure that we meet that goal. And again, the way we do that is going to be heavily biased by our experience. So we're very likely to kind of pick tasks that we are familiar with, that we're comfortable with, or that look easy. Because what's always missing in a quantitative goal is the most important aspect. And that is the business impact. So to me, and again, the business impact is something that we just cannot see in the source code. So to me, any attempt at trying to improve or trying to get situational awareness or trying to quantify technical debt via source code is simply not actionable. There's no way we can act properly on a long list of thousands of issues. And more specifically, technical debt just cannot be calculated from a source code. The thing we can see from the source code with respect to technical debt is maybe the remediation cost. That's something we could estimate from the code. But technical debt goes much deeper than that. Technical debt is invisible in the code. Technical debt is the additional cost of working with that code. At the same time, I do think it's important to be able to have these conversations, because we're always going to have to make a trade-off between improving existing code versus adding new features. And it's a balance that's kind of going to shift over time, depending where we are in our product lifecycle and in our business. And behavioral code analysis is one option here. So finally, what is it? Well, I have this quote from my latest book that I'd like to read for you. And again, behavioral code analysis, it doesn't offer any silver bullets, and it's not intended to replace anything. Instead, the purpose of behavioral code analysis is to complement your existing expertise and allowing you to focus your attention on the parts of the system that are likely to need it the most. And just to be really clear, what I mean when I talk about the system is a combination of code, people, and context. And I hope that I managed to clarify that. The basis of behavioral code analysis is behavioral data. So the idea here is that we can somehow figure out, how do we as software developers interact with the code base that we're working on? How do we as individuals or teams have an impact on the code we're building? And this is data that you all already have. We're just not used to think about it that way. I'm talking about this. I'm talking about our version control data. I find it so fascinating with version control, right? Because it's something virtually every company uses version control. But in most cases, we tend to use version control as like an overly complicated backup system, and then occasionally as a collaboration tool. But in doing so, we have actually built up this absolutely wonderful behavioral data source. So just to have a quick look here at version control, we're going to see many more examples soon. We see that one of the big advantages of version control is that it kind of gives us a time dimension into our code. We can see where we have worked, how frequently we have worked in those parts, right? And how those patterns shifts over time. And I'm going to show you soon how this is something you can use to actually prioritize technical debt. So you don't have 5,000 issues, maybe you end up with 5 that really matter. Another thing that's very fascinating with version control, I'm not going to talk so much about that today, but that is that version control data is actually social data. Because based on version control, you know which developer that worked where. And it's fairly easy to aggregate developers into teams. And you can now reason about the code base from a team perspective, meaning you can actually visualize and measure things like Conway's law, for example. But that's a topic for a separate presentation. Be happy to talk about it later when we get to questions. So with this lengthy introduction, I'm finally done. I've set the stage. Let's look at behavior code analysis in practice on real projects. And to do that, I'm going to have to shift my screen. So let's see here, stop screen share and start again. So you should now be able to see my web browser. And I want to demonstrate the first use case I want to show you is how behavioral code analysis can help you prioritize potential technical debt, can help you prioritize refactorings based on the likely payoff. And I want to start by showing you on a really, really big system, one of the best known open source projects there is, the Linux kernel. The Linux kernel is a very fascinating piece of code, and it's fascinating because it's so large. So a Linux kernel consists of roughly 16, 17 million lines of code. So lots of code. What's even more fascinating, if we look at just the numbers here, we see that the Linux kernel has been developed by more than 15,000 contributors. So my first question to you is, given that you have 16 million lines of code, 15,000 contributors, who has a holistic picture? Most likely no one. And even if we today decide that we're going to dedicate our life to understand the Linux kernel, we will still not be able to keep up with it because a code base at that scale under active development is a moving target. So our knowledge would become outdated pretty quickly. So let's see how behavioral code analysis helps us. The first thing I want to look at is an analysis that I call a hotspot analysis, something I cover in the first chapters of my book. And this is like the starting point of all behavioral code analysis. So what do you see here? Well, you see a visualization of 16 million lines of code. So this is the whole Linux kernel. The way you read this visualization is that each one of these large circles that you see here, they correspond to different top-level folders in the Git repository representing Linux. So if this was one of your code bases, you would recognize the names of these folders as important subsystems or high-level components. It's also an interactive visualization. I use a visualization that I call Enclosure Diagrams to do this. And so I can click on one of these subsystems, I can zoom in, I can see the other folders beneath it, and I can drill even deeper. And once I get to the lowest level of detail, I can see that each file is visualized as a circle here. And you see that some circles are pretty big, others are much smaller. That's because the size of a circle represents the number of lines of code in that module, in that file. And the number of lines of code, it's fascinating because it's an extremely rough metric, right? It's a horrible metric. But what makes it useful is that all other metrics are equally bad. It turns out, if you look at the research, you will see that number of lines of code is actually a decent approximation of the code complexity. And this has been studied, right? There have been a bunch of comparisons with other more elaborate complexity metrics. And so this is like a useful heuristic that if we want to figure out which piece of code is the most complex, we can basically just look at the size here. And the reason I say this is because code complexity, in a behavior code analysis, code complexity is important, but it's the least important thing. Because complexity has this property that it's only a problem when and if we need to deal with it. So what we need to figure out here is that if we have some complex code, do we actually have to work with that code or not? Maybe it's code that has been stable for 5 years. We never need to touch it. Is it really our concern right now? And this is something we can answer by going back to our version control data, right? So we can go to Git and we can pull out statistics and see how often have we made a change to this piece of code? How many commits have we done to each piece of code? And this is what you see in the visualization represented as the color here. So the more red something is, the more commits we have done to that part of the code. And what I call a hotspot is an overlap between these two dimensions. A hotspot is complicated code that we have to work with often. And those are the parts of the code that I typically want to dive into. I want to really understand it and make sure we don't have any hidden technical depth here that we need to be aware of. So let's see what we can find in Linux kernel. I can see here already on this high level, I can see that there is something interesting down here. Let's zoom in and see what this is. i915. So this is the graphic card for from Intel. And the hotspot that we have here is something called Intel Display. So let's dig a little bit deeper. Let's click on that one so we can see a bunch of statistics that we can also pull out of Git. First of all, if we look here to the right, we see that this is quite a massive module. It consists of more than 12,000 lines of code, right? And we can see that during this analysis period that I'm looking at, you can basically select yourself in a behavioral code analysis how far back in time you go. We can see that there are more than 3,000 commits touching just this file. So a lot of development activity. And what this basically means is that any code quality issues that we find in this code are very likely to have a high impact due to the high development activity. So what I can do next is that I can look at different linting results, because the main difference now is that now I have kind of narrowed my problem down. I won't get 5,000 results now, right? I'm narrowing it down to just one file, and I'm expecting that file in a context. I'm expecting it in a behavioral context. So if I want, I can, there is some stuff here I'm going to show you very quickly, but you can basically use any kind of tools you want. You can get a quick overview and see, oh, do we have something overly complicated? Yeah, there are some complex methods in here and so on. So I can make a very quick assessment here and see that, yes, there is indeed some kind of issues inside the Intel display. Now, the question is, of course, yeah, maybe there are some issues, but maybe the team is already aware of this. So the reason they have so many commits here is because they're working on improving the code. Well, this is something that we can get insights into using other behavioral code analysis technique. So what I do here when I find a hotspot is that I go to Git, I pull out each historic revision of that code, and then I measure the code complexity, which could be like the number of if statements, number of logical conditions, or it could just be the number of lines of code over time, and I plot a trend. And you see it down here for the Intel display. So here's the complexity trend. So we see that this file started its life in like 28, 29, something like that. And as you see, it has been an almost linear growth since then. So if I take a step back, just based on the data points that we have so far, we have an most likely overly complicated piece of code that we need to work with all the time. And when we do that, it becomes more and more complicated. So to me, this sounds like some kind of vicious circle that I would like to break. So to me, it would be very clear that, you know, if we should refactor anything, maybe this is a very good starting point, because it's so likely to have a continued business impact. The question is, of course, who would like to have that refactoring task? This is 12,000 lines of code. That's a gigantic file, right? And the thing is that taking on a refactoring at that scale is going to be a huge risk, because what's very likely to happen is that there's going to be a team that kind of branches out, they work on redesigning and refactoring that, and they are never, ever going to be able to deliver it back. Because in the meantime, all their colleagues have been making bug fixes or adding new features to the same area. So what I tend to recommend is to, when you refactor, when you redesign, always break it down to the smallest possible scope. And there's one way of doing that, guided by behavioral code analysis, is something I call an X-ray analysis. And this is the reason why I call my book Software Design X-rays. So inside here in this tool I'm using, in CodeScene, the tool, I'm just going to click this button, and I'm going to explain what actually happens. So what happens now is that I go to Git, I pull out this file and I parse it into the separate functions inside it. And then I look at the Git log. What do each commit hit over time? And I sum it up so that I can get hotspots at a function level. And this is the list I use to prioritize a starting point for my refactorings when inspecting code that I'm not necessarily familiar with. So let's see why. If we look here, we see that the number one local hotspot inside this large file, inside this large Intel display with 12,000 lines of code, is something called Intel 0TC page flip. And we see that over the past year, it has been worked on 79 times, so 79 commits just to this file. So that means like almost twice a week, some developer is impacted by the excess complexity here. And we can kind of get a very rough estimate on how complex that piece of code is if we look at the last column here. So this is a metric called Cyclomatic Complexity. And some of you might be familiar with it. It's a relatively common metric. And what that metric does is basically that it counts the number of execution paths through that function. So each time you have an if statement, +1. Each time you have a loop, +1, and so on. You sum them up. And cyclomatic complexity, the reason I tend to use it is because it kind of represents how many unit tests would I need to cover just that function. So in this case, I would need 45 different unit tests. So that kind of tells me something about the complexity there, right? So there's probably a great opportunity to improve that code and modularize it a bit. And now, I'm going to show you a bunch of other things. Before I continue, I'd like to show you why hotspots work so well to prioritize technical depth and to prioritize refactorings. If we go here, this is just some descriptive data. What you see here on the x-axis, it's each function inside this large hotspot inside the Intel display. And we see that there are like 450 functions. These functions are sorted according to their change frequency that you see on the y-axis. That is the number of commits that touch that very function. And what you see in this graph is kind of fascinating. Like more than half of the file is stable. So this is code that was written once. We never had to touch it. We never had to work on it or extend it. So this is very, very stable code. And again, if you look at software research, you will see that code stability is, code that hasn't been touched in a year is much more likely to be bug-free than code that you have worked on recently. So having code that's stable and just does its job, just works, that's also a very nice property. So even if there might be some code quality issues down here in this long tail, it's code quality issues I would be prepared to live with because the code is stable. We don't need to work on it, right? So maybe they're not having a big impact on us. On the other hand, we can clearly see here, I can even zoom in a little bit, that most of our work is in a relatively small part of the overall file. We see in particular, there's like 1 or 2 functions that really stand out. So if I want to improve anything, I should definitely focus at the head of the curve here. And that's exactly what a hotspot analysis does for you. It kind of allows you to zoom in on the parts of the code that are likely to have the largest impact. And before I continue, let me just sum up what we did. So we identified, we can, of course, we can always dig into the code and look at that, but I don't want to detour too much. But now, what we did was basically, we identified a very likely refactoring candidate. It's a fairly large function, 238 lines of code. But 238 lines of code is much less than 12,000 lines of code, which was size of the total Intel display hotspot. And it's definitely less than 16 million lines of code, which was size of the total Linux kernel. So more importantly, we are now at the level where we can act upon this information and do a focused refactoring based on data from how we actually work with the code as an organization. All right. Now that we're in the Linux kernel, I want to show you another thing that you can do with version control data. And this happens to be one of my favorite analyses. It's a little bit more advanced, but it's really, really cool because it's something you just cannot do on source code analysis level. It's something I call change coupling. So let me click here and try to walk you through what you see. So you're probably all familiar with coupling, right? And when we developers, when we talk about coupling, what we typically mean is some kind of dependency. So I have some code over here. I'm using some code over here. Now those two pieces of code, they kind of depend upon each other, right? We have a dependency between them. And those kind of physical dependencies, it's something that you can measure from source code, right? You can pick up the code and you can see that, yeah, we're making a reference to the instance over here. Change coupling is very different because it's invisible in the code. It's something you can only measure from version control data. So what we do here is that we go to version control and we look at patterns in how we as developers work with the code. So let's pick the first example here. We have two functions here. One is called Intel Finish Page Flip CS, and the other one is called Intel Finish Page Flip MMIO. We can kind of tell, based on name that these seem to be related. And what the version control data tells us here is that when I, as a developer, make a change to one of these functions, I have a predictable modification to the other one as well, in 100% of all commits I do. And I can see that this is not just a fluke. It's something that has happened repeatedly. In fact, it has happened 11 times. So that means I, as a developer, when I want to modify one of these functions, I've always had to modify the other one as well. A very likely explanation to why that's the case is given here in the last column called similarity. So what I do here is simply I run a copy-paste detection algorithm on top of those two functions, because copy-paste, a dear old friend of mine, is a very likely explanation that you have these repeated modification patterns. And that copy-paste algorithm claims that, yeah, there's a 99% similarity between these two functions. And when I find something like that, I always want to look at the code. So let's do that. And I know that not all of you are C programmers, but let's see anyway. Can you spot any subtle similarities? Yeah, that's right. There's a single character difference over here. There's a single character difference. All the other code is identical. But this is not something that I would be so concerned about, because it's very easy to see that, and it's kind of the refactoring. If we want to refactor, is easy as well. I'm much more concerned about the next one here. So here we have two other functions. Again, you modify one, you have a predicted modification, the other one in 100% of the cases. And it has happened 21 times. So let's do a diff here. And what I'm going to show you now is the most expensive code that you can ever have. And the reason I say this is because, again, if we look at the diff here, just overall pattern, we see that in the code to the left, there's an if statement here, a condition that's absent from the code on the right. And the reason I say this is the most expensive code you can have is because what happens now for me as a developer, when I go into this code, I kind of need to question every single time, is this, oh, sorry, I lost one of my AirPods. Is this a bug fix that we added in one place and forgot to add in the code to the right so that we have a defect here? Or is it a context-specific check that can only occur within the calling context of this function? Without more information, I just don't know, right? So when I see code like this, a simple thing to do would be to kind of refactor it, extract and abstract away the similarities, and encapsulate the context that varies. That way you can kind of communicate if this is indeed a context-specific thing to a developer coming after you. And that's going to save you and the team a lot of time. There's so much else I could tell about this, but I want to make sure we have time to get questions. And if there are any questions, maybe I can drill deeper and show something else. So I'm going to stop my screen share and open up for anything you would like to ask me. And I hope I managed to kind of bring across at least this use case with how do you prioritize technical debt using behavioral code analysis.
Yep, thank you, Adam. I think we have questions from Valerio. So Valerio, could you unmute? I think you have plenty of questions, so at least 3.
Yes. So I have some questions starting from the beginning. The first one is about the map you showed, about the map of the UK you showed. And I want to ask you if, so as you already said, this impact, this perception is the same for the part of the software we are familiar with. And so I want to ask if this impact with the estimations we do. And if the answer is yes, what is for you the best way to give a balanced estimation for that part?
Yeah, so it definitely has a huge impact on estimation. And in particular, it's very easy to kind of underestimate the complexity of parts of the code that we're familiar with. So it's particularly challenging if we do estimates for someone else. And what I've seen happen very often is that it's also very easy to make the opposite mistake, to kind of overestimate the complexity of code that we're not familiar with. So I have this kind of fascinating thing I experienced a couple of years ago. So I went to one of my clients and I did a workshop for them where we analyzed their code. We looked at their hotspots, and they had two systems, and both of them look fairly good. So in the commercial tooling I'm using, I also have some additional metrics that kind of give you a code health estimate and things like that. And it looked very good. And then towards the end, one of them told me that, we actually have one more code base. So I said, all right, let's look at that one. And they said that we don't have to do it. We know it's a mess. We don't want to touch it. So I said, now we have to look at it, right? So we analyzed that one as well. And guess what? The numbers came out just as good as the other code bases. So technically, there was no distinction between them. They were all high quality code. But then I figured out that the reason that the third code base was considered to be so much more complicated was because it was actually written by a different team in a different part of the organization that had since been disbanded. And this team had simply inherited the code. So the reason they thought it was overly complicated was simply because they lacked familiarity with both the domain and the solution. And doing estimates in that scenario, it's simply going to be dangerous. So I'm personally not a big fan of estimates. I'm a big fan of priorities. So what I try to do internally is that we always have very clear priorities, but I'm very, very careful with estimating things. Because if something's worth doing, it's worth doing. And the important thing is that you start on it. What I also do is that I make sure that everyone involved, all stakeholders, the development teams, non-technical stakeholders, that we share the same understanding. So regularly, and like team retrospectives is a great way of doing this, do a hotspot analysis, bring it up. You can even filter it for your team and discuss it. Because at that point in time, you have all the stories that you worked on fresh in your head, and you can kind of see how they impacted your code base. And that can help you get a lot of information into the next iteration you do. So it's something that can help you avoid bias, right? Can help you avoid that.
Yeah. Okay, thank you. Next question is, yes, let's say, how do you use the code scene tool in your daily job?
Yeah, so I use it in multiple ways. So we look at it regularly. So like once a week, we kind of, tend to look at it just to stay on top of it, have the overall picture. And what we do most of the time is that we have it integrated into our build pipelines. So we use it a lot to kind of support things like code reviews, because code reviews, I like code reviews, but they can very easily become a time sink. So by using a behavioral code analysis as input to a code review, you know that, all right, these are the parts I need to focus on. There are things that the tool can capture for me, so I don't even have to spend time on it. So this has been one of the success factors for us with integrating the specific tool.
Okay, thank you. And my last question is, yes, about the last part you showed. if this tool has the possibility to compare classes as well, apart the functions.
Oh, I almost need to show you. I hope I have that analysis because this is one of my favorites. I really love this one. Let's see if I can share my screen again. Can you see my screen?
Yeah.
So let me show you something cool. So this is Spinnaker. It's on open source code base developed by Google and Netflix. It's like some kind of CI/CD system for the cloud. And what's fascinating about it is that it's a microservice architecture. So all of these bubbles that you see here in the hotspot analysis, like here, Roscoe, Echo, and so on, they are separate services, and they are implemented in separate Git repositories. And what's so fascinating about version control is that it's completely language neutral, because these services, they're implemented in a bunch of different programming languages as well. So maybe I can add a little bit more filter so you can see. So basically what you see here is that each color corresponds to a separate programming language. So we have Groovy code over here, Java code here, TypeScript, Scala, Go, all different things. And with the change coupling, you can actually find dependencies between code written in different languages, even if it's located in different repos. So let's have a quick look at that. So I can look here. And I can simply see what kind of dependencies do I have across repositories. Let's actually add a filter to make that a little bit simpler. So here we go. So here I can kind of catch dependencies at the file level between different parts of the application. And I could even X-ray it and see which functions inside this service change with functions over here. So you can do a lot of really interesting things with version control. Hope that answered the question.
Yes, thank you a lot.
We have our next question is from Cedric. Cedric, could you unmute?
Yes. Yeah, I just had one question. It was about using codesyn on test code. Is it the same way to use the tool? Does it make sense? Yeah, was just a curiosity.
It's a fantastic question. I actually have a whole paragraph or a subchapter in my book, Softwares and X-Rays, that I called "There is no such thing as just test code." Because in my perspective, if we as developers, it's very common that we make a mental divide between application code that we know it's important, we keep it clean, easy to evolve, easy to maintain. And then we have the test code where very often we're happy if we get around to write any of it at all. And I think that's really dangerous, because if your tests lacking quality, they will hold back your overall efforts. And what could be a great support for you, what could be a great safety net, now suddenly becomes a time sink. So I would strongly recommend to always analyze test code as well, and to put the same quality bar on your tests as you would do on the application code. I try myself to not make any distinction. So I hope that they answer the question.
Yes, thank you.
I have one little question about CodeSyn itself as a product. We also the product in is great, and we are looking ourselves to use some of the free open source projects. Our colleague Ivan proposed those, and they're really great. We plan to introduce them to use the open source version. However, the CodeSyn comes with a complete solution with stuff. You don't have to play around and understand stuff. Imagine today I'm super impressed. I'm a developer, I'm super impressed. I'm a tech lead, it doesn't matter. I'm going to the management and say, I want to use CodeSyn. How, from your perspective, what would be the way to convince a project manager or a product manager or a business person, very important, it's not technical person, to spend money on CodeSyn?
Yeah, that's a great question. I won't claim that I have all the answers, but I have some.
Yeah, you have some inputs, yes.
Yeah, let me share a link with you. It's a PDF document I published a while ago, which is how to calculate the costs of the business costs of technical debt. So I'm going to paste it in the chat in case you want to have a look. In particular, when talking to non-technical stakeholders, because very often we need to go to them to, you know, get the credit card. And what I typically do is I try to quantify what's the cost, what's the risk of not having those insights. And what you can do when it comes to technical debt is that technical debt leads to a number of consequences that have a huge business impact. And one of those consequences that is quantifiable is unplanned work. So what is unplanned work? It's basically anything that isn't a feature, anything that we don't have in a roadmap. So things like bugs, production failures, all that kind of stuff. So if you track that, and many companies today use Jira, right? So maybe you just have a specific issue type in Jira, right? For that says bugs, defects. What you can do with a tool like Codesin is that you can quantify that, and you can see how many percentage of my work is spent doing unplanned work. And what's so great about this is that there's actually some research on what's a good level of unplanned work. And it turns out the good level is 15 and below. You can most likely never get to 0 in software, but as soon as you're above 15%, it simply means that you have an untapped capacity. This is what I would explain to a manager is that, yeah, let's say you have 40% unplanned work. That basically means you're paying for 100 developers and you get the equivalent of 60 developers out of it because 40% of your capacity is wasted. So then you also have some kind of return on investment that you can show them that, hey, maybe if we can identify our top hotspots, maybe we can improve those parts of the code. Maybe we can get that unplanned work down from 40% to just 20. That would be a clear win for us. And everyone else would be happy as well, right? Because it improves the job satisfaction as well to work with high quality stuff. So that was a brief summary. Do you think that helps?
I see. Yeah, it does. I see the perspective from which you are looking at. Yes. And I was thinking as well at some moment that measuring as well how much bugs you have a day, how much builds are failing due to bugs, how much time it takes to fix a bug from the moment of declaration till the moment of putting it in closed, regardless of the solution. So this actually, the old kind of ratios are speaking as well for the problems that are existing in the team that can be solved just by analyzing the code. You know, with tools like Codesin, for example, in order to identify the hotspots and the problematic spots.
Yeah, exactly. And, you know, that's one way I'm doing it as well. So in Codesin, we integrate with Jira and Azure DevOps and all those tools. And we bring in information like that. So when you look at the hotspot, you can also get detailed defect statistics and see that, hey, we have like 50% of the work here is bug fixes, which again, it's a business risk. We just need to kind of explain that. So yeah, I agree with that. And I also think it's important when, I don't want to talk too much about that because it's one of this feature we're going to open up for open source projects as well very soon. But we have this integration with pull requests where you can use Codesin as a quality gate. And I think that's important because the number one thing you do to address technical debt is not that you start refactoring code. The number one thing you do is that you put a quality bar on what's already there. You don't take on more technical debt, right? So that's why I think that's important. Even if you don't, even if you don't do anything else, at least do that. And I think that's already a benefit.
Yeah, I remember this quote over a big hospital back in my country. The best cure is the prevention. Indeed.
Okay. We have another question from Guillaume. Yeah, Guillaume.
Hello, everybody. Yeah, I do have one question. So with Codesin, you showed us that you are able to spot the different, the sensitive points of a solution. Now on a project, we know that we have people coming and going. We have everybody know a specific piece of the product. How would you recommend, what would be your advice to help a team to keep the knowledge on a specific solution to make sure that we try to have accurate estimates? And also, would you try to have, let's say, a specialist in the product to make sure that we keep the knowledge on every piece of it? I do not know if you had experiences like that in the past.
Yes, I did. It's fairly common. I actually have a blog post that touches upon it. Let me see if I can dig that one out, and you can have a deeper look afterwards. I'm going to try to answer the question now as well. So here we go. Let me paste that one in the chat. Yeah, so in general, knowledge is what I tend to refer to as system mastery. How well does the current team know the product they're building? And it's a really, really important factor. I would say it's just as important, or if not more important, than any technical properties of the code. So behavioral code analysis can actually help us there. Let me show you how it looks. You can see my screen again, right?
Yes.
Yep.
So let's pick this one. So this is another open source project. So one analysis that I use is this one. It's something we call it knowledge risks. And basically what to do here is that we identify parts of the code that are written only by one person. And then we correlate that with some of the technical properties, like, you know, is the complexity trend going upwards? And this might be a growing problem, or what does it look like? And the idea here is not to do any micromanagement, but to prevent risk. So in this code base, for example, let's see what do we have here. So here's one package called BALCL. And what the colors tell me is that yellow means that this is written by just one developer. So we have like a key personnel dependency. So if that person leaves, we might have to learn that ourselves. But what you can also do is that you can then combine this with the hotspots and the code health metric that I didn't talk about to identify things like this that are clear risks. So this is what I refer to as a knowledge island in a complex hotspot. So it simply means that we have a complicated piece of code that we work on all the time. So it's very likely that we will continue to work on it. And it's only one developer who works there. So I would try, if I have that pattern, I would try to proactively maybe pair that person together with another developer so that you can refactor it together and kind of mitigate a potential risk. Because that person, most likely, they would like to go on vacation, even if they stay with the team, right? And you really don't want to have gaps like this. So that's the way I would try to manage it. Did that answer your question?
Oh, yes. Thank you very much.
I have another question about the unplanned work. I didn't get how CodeSyn helps with that. So it helps to identify the unplanned work, or is about something else?
Yeah. So let's see. Maybe I can. I hope I have some demo data. I'm actually not sure because there are not that many open source projects with Jira. Maybe I can show you an example. I think this one. So here's an example. This is at the system level, so it's for all code within this repository. And what you see here is a trend line starting in 2019 and going to the present day. And what I can see here is the data for each month. So I see here, for example, in August, we spent 40% of our time doing unplanned work. More recently, it's down to 37, but it's still a high number because I have this baseline with 15 that I know is good, right? So there is some excess technical, there is some excess unplanned work going on here. I don't know why, but what I know, from research and a lot based on the great work done in the Accelerate book and the State of DevOps, is that if I improve a bunch of practices, if I manage technical debt, if I have a loosely coupled architecture, then it's very likely they can bring this number down. So this would be something I would maybe report on to my managers and say that, hey, look, give us a month to refactor and we're going to show you what we can do. And maybe you can bring it down to 25. And so it's more something you use for communication rather than to make your decisions on.
But how do you identify it? Do you put something special in let's say if you use Git a special tag or.
Yeah, exactly. That's how. That's basically how we do it. So you can see. Let's see here. You can basically, instead of looking at, let me just increase this one so you can see. Instead of looking at hotspots, you can look at cost hotspots. Where do I spend most of my development time, down to like your file level. You can also see where are my bug fixes happening. And the way you do this is CodeSyn needs to know. It needs to have a link from a commit to Jira, Trello, or Azure DevOps, right? And that link can be either in the commit message. You just put the stamp there. You have like a pre-commit to Code and Git that inserts it, or it can be in the branch name, right? So if CodeSyn knows that this branch references this Jira ticket, we know that all commits below it are related to that one. So that's how it works in practice.
Okay, thank you. Okay, yes. So this requires that, let's say, the unplanned work is correctly managed in Jira. Otherwise, it will not, of course, so by consequence, will not be displayed well in the tool.
And basically, the only hard requirement is that, yes, you need to identify and label those issues. Otherwise, we don't have any data. And there needs to be a link between them. But then CodeSyn can do a lot of the heavy lifting, like you don't have to track time and stuff like that. CodeSyn can kind of estimate the development time for you and things like that.
Okay, thanks again.
Okay, we are running out of time, so sorry guys, but we need to close here. Thank you for coming today. Thank you, Adam. Thank you very much for your great talks and answer to our questions. It was really great. We will make maybe a little survey to gather your feedback as well. But really good to have you today. And I just want to spend a few seconds just to explain what is going on next. So we'll have another talk at the end of this month. So it will be more a hands-on session. It will be in F#. The idea will be to make some domain modeling with F#. So if you don't know the language, don't worry. You can come. You will understand it really quickly. So it will be a really practical session. And the next one will be we will make an architectural kata with Johan Martinson. So the idea is to make the same kind of stuff that we do with Code Kata, but on the architecture level. So it will be really interesting, and you will discover how in this session. So it will be a beginning of May, I think. So we'll announce it on Meetup. So just stay in touch. And thank you again, Adam. Thank you. It was really great.
Thanks a lot. Thank you for having me, and have a great day, everyone. Really nice seeing you.
Thanks a lot.
Thank you again.
See you soon.
Thank you.
Cheers.
Bye-bye.
Bye.
Thank you.
Bye.
Bye.
Bye-bye.